this is a simple but very efficient way to illustrate the concept of vibration isolation. Suppose now that this here is an object that needs to be protected from vibration, but my hand is a source of vibration. So when I mount the object that needs protection against vibration rigidly to my hand, then as you can see, my hand transmits vibrations very efficiently to the object here. Now, if I instead here mount this object here elastically with this elastic string to the source, as you can see now, if I oscillate the source with a very, very low frequency, the object still follows the source closely in its motion. But if I increase the frequency of motion, then as you can see, I hope the object does not follow the source in its vibrations. Okay, it vibrates a little, but not much. If I make my source oscillate slower, and then as you can see at this frequency, my hand almost, well, the source almost does not move at all, but the object vibrates heavily. So now we have resonance. So that is something that we need to take care of to avoid resonant conditions. Once again, very high frequencies, then the object is almost at rest and the source vibrates heavily. So this is something that we are going to talk more about in the upcoming presentation.
In this part of the course, we are going to discuss different methods to reduce noise and vibration. And as you know, the whole course is based on the assumption of linear systems. So that means if we use this frequency response function approach, that in this case, for instance, where we have a number of sources contributing to the noise in a cabin of this ship, we can represent the noise contributions as this linear relationship. So we have sources indicated with F here, and the path indicated with H, and the receiving, the sound pressure at the receiver indicated with P here. Source, path, and receiver. So, in order to reduce the response, the sound pressure response, we can either reduce the source contributions by reducing the sources. In this case, the propeller contribution. In this case, the contribution from the transmission gears, and in this case, the contribution from the internal processes of the diesel engine. So that is one way to do it, to try to modify the different sources. The other way is to reduce the paths that the sources contributions travel along towards the receiver. So that is what we are going to focus on in this presentation. So we have now the task then to investigate how we can and what the effect is, what the influence is of when we try to reduce the transmission along the different paths between the sources and the receiver. One way to do this is to use vibration isolation. And the purpose of vibration isolation is, as the name indicates, to reduce the vibration transmission from the source to the receiver. One important transmission path for acoustic noise between the source and the receiver is that it propagates as vibrations at parts of the path. And that is what we are going to focus on in vibration isolation. So we try to cut off this path by introducing a vibration isolator between the source and the foundation. So this is one illustration here. So we have a vibrating source and the foundation that receives the part of the vibration energy that the source emits here. So if we introduce this red thing here, the vibration isolator, we hope that the situation will be improved and that the vibration is restricted to the source part here. The foundation should not vibrate. So no transmission or much smaller transmission through the vibration isolator. That is the purpose of vibration isolation. So in practice, this can look like this. So if this is a machine, we mount the machine on the foundation via this kind of vibration isolators, often manufactured in rubber, weak rubber. Another method to reduce the, well, or to reduce the transmission of noise along a path is to use silencers. Silencers, of course, aims to reduce the acoustic energy transfer along the path from a source to a receiver. So if you have, for instance, a source here, it can be a ventilation fan, or it can be a combustion engine, or it can be, well, anything that produces gas or liquid flow pulsations in a duct here. Because when this volume flow pulsation reaches the outlet here, then it will transmit as sound and reach the receiver. So a duct silencer, if you install it somewhere along the duct, it will hopefully reduce the sound power emitted and the sound pressure in the observation point at the receiver. Here's a typical silencer for a small machine, a chainsaw or something like that, lawn mower. Here's another example, a car for a combustion engine. We have the inlet here and the exhaust outlet here. And then these things inside here are designed then to reduce the noise at different frequency ranges. Another example is to change the sound radiation properties of the different surfaces that radiate noise. When the surface vibrates, it will radiate noise, and the properties of these radiating surfaces determines how efficiently the sound is radiated from the surfaces. So if you can reduce the radiated sound power by somehow modifying the vibrating surfaces, then you have reached your goal to reduce the noise radiation. One way, for instance, is to work with the coincidence frequency of the different radiation surfaces and increase the coincidence frequency. Then all vibrations with lower frequency than this coincidence frequency will reduce more inefficiently and produce less noise. This is one typical example. If you, for instance, have highly radiating surfaces on machines like this, then you can try to exchange these surfaces with perforated surfaces. On a perforated surface or plating has much less radiation efficiency than a solid surface has. So that is one possible method to use. So now we are going to exemplify the two ways actually to reduce the transmission path contributions. So it's two examples here. As you can see here, we have a machine. This is a machine that produces noise, and we have two capsules here. So we are going to place these two, first one and then the second one, over the machine here. And then, of course, the noise that the machine radiates and that reaches the microphone or the listener position will be reduced, because it's difficult for sound to penetrate these capsules. So now you can hear so 83 dBA, A-weighted sound pressure level, was the sound pressure level, the A-weighted sound pressure level with the machine in itself running. So now we will try the same thing, but with the first capsule, encapsulation put on top of the machine. And this is what the result will be.
Så här ser det ut nu, och som ni kanske hör så låter det betydligt mindre. Nu kommer jag och ska vi läsa av vad ljudnivån blir. Ja, som ni ser så blev ljudnivån omkring 64 till 65 decibel.
So considerably lower, as you can see, almost 20 dB reduction, 20 dBA reduction of the sound, A-weighted sound pressure level. Next thing is to try with two enclosures put on top of the machine. Then it will look like this.
Ja, så här ser det ut nu. Jag hör i alla fall ingen större skillnad, så vi får läsa av och se vad resultatet blir. I stort sett detsamma som med enkelkapslingen, så ingen förändring alltså.
So no change, pretty much the same. So a second enclosure did not change the sound pressure level at the observation point at all. So obviously we have reached the end of the encapsulation efficiency. So then we should try the next option we have.
Det vi ska göra nu, det är att se om vibrationsisolering av maskinen kan ge en förbättring. Den här svarta, den här lilla metallramen där med svarta slangbitar i hörnen, det är en vibrationsisolering. Så att jag ska ställa borrmaskinen på den där och ska vi se om vi får någon skillnad. Så nu tar vi och ställer den vid sidan av här. Och ställer upp den här på det där viset. Och sen ska vi mäta nu ljudtrycksnivån utan kapsel och sen med kapsel. Får vi se vad som händer. Här har vi först fallet utan kapsel och då läser vi av ungefär 83 decibel. Ingen skillnad jämfört med fallet utan vibrationsisolering.
So the vibration isolation in itself didn't change the sound pressure level at all at the observation point. So the next step now is to combine these two methods, vibration isolation and enclosures. So we try now to put the single enclosure upon the vibration isolated machine. And this is what we get then.
Så det här är fallet med vibrationsisolering och med kapsel. Ska vi se vad mätresultatet blir. Omkring mellan 53 och 54 decibel verkar det bli. En väsentlig förbättring alltså jämfört med fallet bara kapsel. Vad beror det här på? Det får ni ta och fundera på en stund. Ska vi ta och diskutera det tillsammans sen.
So, a drastic improvement actually from the case with only a single enclosure. So now we have, roughly speaking, 30 dBA reduction in the A-weighted sound pressure level. So that's very good. So what we can conclude here from this experiment is that the enclosures, they reduce something that we call the airborne path. That is the path, the transmission path of the airborne sound radiated directly from the machine to the air. That is the sound that is reduced by the enclosures. But when we place one of these enclosures on the over the machine, then we have reduced it so much that other contributions from the machine becomes important. And the second transmission path from the machine to the receiver is called the structure-borne path. And that is actually when the machine is played, it vibrates, it starts vibrations in the plate and the tabletop it stands upon. And the plate and tabletop, because they vibrate, they will also emit noise. And that is the structure-borne, the vibration-borne path. And this path, this contribution becomes much stronger now. No, it does not become stronger, but it becomes dominant over the remaining airborne path. So in order to improve the situation now, we must reduce the structure-borne path. And this is where the vibration isolation comes in, because the vibration isolation reduces the structure-borne path, since it reduces the vibration on the plate and the tabletop. And if we combine these two, then we have reduced both these important transmission paths, the airborne path and the structure-borne path. And then we can reach very high level noise reductions. So this also pinpoints the importance for an acoustician to be aware of what are the transmission paths that is important in the noise problem. If you don't know what the important transmission paths are, then it's like trial and error. A modification you do may be totally useless.